Today's discussion is about how to assign the nonlinear properties to various structural elements like column, beam, beam column joint, masonry, etc. Nonlinear modeling. Actually, in the software, first of all, we have to create a model that is a conventional model. And then this model is required to convert into nonlinear model, right? Nonlinear model. Now, why this model is required? So nonlinear modeling is required to perform the nonlinear analysis, and nonlinear analysis is the basis of perform-based design. Perform-based design, which is also known as a capacity-based design, which estimate the response of the structure in the linear as well as the non-linear range, that is inelastic range. And inelastic range is very important because inelastic behavior of the structure dissipate the seismic energy in a large way. And to estimate the nonlinear behavior, we require a nonlinear method, and this which also demands the nonlinear modeling. Now, to the conventional model, we have to assign certain properties. So first type of the nonlinearity, what is called as a material nonlinearity, and number two is called as a geometric nonlinearity. Now we'll see in depth about these two type of the nonlinearity. Now this is a building and which has a different elements as a slab, column, beam. Masonry is not shown, but sometimes masonry is also there. And then important is the beam column joint. Now, whenever the nonlinearity is to be assigned, so that point is there. So the user must know how these particular different elements fall under the seismic loading, right? And accordingly, we have to assign the nonlinear property. So these nonlinear property should address the failure of that particular element. Normally, in the moment resisting frames, the members fails under shear and as well as flexure. Okay, so this type of the nonlinearity we have to assign. Remember, any nonlinearity is not to be assigned for the slab. Okay, because in the seismic analysis, we are assuming slab as a rigid member, okay, rigid diaphragm, and it is just transferring the seismic forces to the various frames, different lateral frames. So therefore, the slab is, any nonlinearity is not to be assigned to the slab. Then if the beam is there, so to the beam, we have to assign the nonlinearity, flexure nonlinearity as well as shear. Column also fails under flexure shear. Joint fails only shear. It is a brittle failure. Shear wall, it's failed under flexure and shear. And masonry, if the masonry is there, and then in that case, the masonry fails under axial, in the axial manner only. Now, why the nonlinear modeling is required, or why the nonlinear analysis? Building structures, as shown in the photos, especially high-rise buildings, so they are normally of unusual configurations. Some structures are which are resting on the sloping ground. So therefore, the response of this particular structure during earthquake is not a symmetrical response. Okay, so therefore, the twisting type of the behavior is there. And to address this type of behavior, and this is possible only by the nonlinear analysis. And the nonlinear analysis required nonlinear modeling. So therefore, capacity-based design, which is the new recently developed design philosophy. So in that, nonlinear analysis and nonlinear modeling is most important. The user, how he assign the nonlinearity correctly. So based on that, the result will differs. Now this is the chart showing the complete nonlinearity to be assigned to the different members. Okay. Now, first is the nonlinear modeling. To create a nonlinear modeling, so we have to assign the two things. One is we have to assign the material nonlinearity. We have to assign the material nonlinearity, and number two, we have to assign the geometric nonlinearity. Okay. So the material nonlinearity. So what is the meaning of this? It is a relation between the material stress and strain across the section. The behavior is nonlinear. Okay, so that is meant by material nonlinearity. Okay, and this particular nonlinearity we can assign by two ways, either by means of a lumped plasticity approach or a distributed plasticity approach. In the case of lumped plasticity approach, this nonlinearity is assigned to a specific portion of the element. Okay, so specific portion, that means which are most critical during earthquake, which are most critical or likely to be failed during earthquake. So which is that portion for a beam and column at the ends. Okay, at the ends, mostly during earthquake, there is a failure. So the nonlinearity is to be assigned only that portion. So this particular approach, it is called as a lumped. And distributed plasticity approach, in the sense we have to assign the nonlinearity either for a complete length of the member or complete area of the member. That is called the distributed plasticity approach. The research shows that either go for lumped plasticity approach or distributed plasticity approach, there is no much difference in the analysis, nonlinear analysis. Then second approach is the geometric nonlinearity. So geometric nonlinearity, it means that the relation between strain and displacement is nonlinear. And in seismic nonlinearity, so this strain displacement or geometric nonlinearity is known as a P delta effect. Okay, P delta effect. Now, the P delta effect, let me clear here only. There are some softwares like a SAP 2000, so where the user need not require to do any calculation for P delta effect. So there are ready-made options are available. Okay, so whether you want to include P delta effect in the analysis or you don't want to include the P delta effect. Sometimes the P delta effect is not significant. Okay, so in that case, the P delta effect, you can neglect it. So you just choose the option of none. Okay, and if it is significant, so significant and non-significant, that means user must be well aware about the P delta effect and it's whether it is a to be considered or not considered, not to be considered. Okay, so then in that case, so there is not, in short, just there is not necessary to do much more calculation, just ready-madely available options, none or you want to include it. That is this thing. Now, in detail about the lumped plasticity, we'll discuss. Now, these are the basis of lumped plasticity approach, why the nonlinearity is to be assigned at the ends only. So like this, there are many photos are there. In the past earthquake, there are many photos you can see also. That is, the failure is observed at the ends of the beams and columns. Okay, most of this. And either this failure is a shear failure or sometimes it is a ductile failure. So therefore, the nonlinearity is to be assigned at the ends. This is the one reason. This is the one reason. And second reason is that if you see the bending moment diagram of a frame under lateral loading, so the bending moment is maximum at the ends only. So that is flexural stresses are concentrated under lateral loading at the ends. So this is for the column and this is for the beams. So therefore, the beams and columns, since the flexural stress concentration is more at the ends only under lateral loading, so therefore these portions are critical and the nonlinearity is to be assigned at the ends. Now, this is the lumped plasticity properties, how it is to be estimated. So this is one, the portion of a beam, and the nonlinearity in the case of lumped plasticity, we are assigning at the ends. That means we are assuming this particular portion as the rigid zone. So this is left side rigid zone. This is a right side rigid zone. And in between, this is assumed as a elastic. This is assumed as elastic. And we have to give more focus on this particular portion, left portion and right portion. Now here to define the nonlinearity, okay, there are two options. There are two options are there. First is there are some ready-made hinges are there. Ready-made hinges which are available in the software. What is called as the auto hinge. Okay, it is called the auto hinge. So just select a appropriate hinge and just assign here, because this is called an auto hinge. And second is that if the auto hinge to this particular element is not available, okay, if the element is not a conventional type, so auto hinges may not be available. So in that case, the user required to calculate the properties of the hinge and then assign. So this is called as a user defined hinges. Okay, user defined hinges. But for the both categories, that is either for auto hinge or a user defined hinge, the moment rotation behavior. So the user must know, or he must be very much clear about the concept of the hinge behavior. Okay, so here the one curve is shown. So this is a hinge behavior shown in the document FEMA 356, Federal Emergency Management Agency 356. This is the moment rotation behavior. So what this particular curve is, in the next slide I will explain what is meant by moment rotation behavior. So this is a behavior that is in the element, column or beam, as the moment goes on increasing, because of the lateral loading, as the moment goes on increasing, what is the change in the rotation? What is the change in the rotation? That is represented by means of a graph. So that is a moment rotation behavior. Okay, so this is the actual behavior. Actual behavior is not a straight line. This is a curve. Okay, and then afterwards, this curve is converted into a bilinear curve. And the blue line shows the bilinear curve. And once we get the bilinear curve, then the different parameters, the value we can calculate, the yield, rotation, ultimate rotation, then yield moment and ultimate moment. These value we will get from this particular bilinear curve. And this is known as a moment rotation curve. And this moment rotation curve depends on so many parameters, that is properties of the section. Okay, which property? Here it is there. So it depends on the section size. It depends on this the grade of the material, grade of the steel, grade of the concrete. So these are the properties required to define this particular curve. Now in the graph, two behaviors are shown. First is the hinge behavior shown here. So this is a moment rotation behavior for a flexural hinge. So in the beam or in the column, whenever there is a flexural type of the flexural failure, to address that failure, we have to assign the hinge is of this type, first type. Okay, so it is also called as a ductile hinge. Okay, it is called a ductile because the curve is a straight line up to B point, and from B point, okay, it is a rising length and it fills here. So this is called as an inelastic deformation. So in this particular behavior, there is a significant inelastic behavior, and therefore it shows this particular hinge property shows the ductile behavior, ductile properties. Okay, so this is the standard moment rotation behavior for the flexural hinge. Okay, for a flexural hinge. And second, if the failure is a shear failure, if the failure is a shear failure, then we have to assign the shear hinge. We have to assign shear hinge. And the shear failure is always a brittle failure, right? Brittle failure. So therefore, once the force in the member, shear force in the member reaches to its maximum shear resisting capacity, so at that instant, it shows the failure. Okay, it shows the failure. So comparison between this first curve and second curve is that here this is a B point, this is called as a B point, and this is called as a C point. Okay, but for the second curve, B point and C point is one and same. Okay, so there is no ductility. Inelastic deformation is not there, therefore it is called as the brittle failure. So these are the two hinge properties to be assigned for the at the ends of beam and column. Now, how to assign it? See, for example, this is a column, and another I will take this as a beam. I will take this as a beam. Now, this is the end of the member. This is the end of the member, and this is the end of the member. Okay. Now, here at the end of the column, we have to assign one flexural hinge. Flexural hinge. At the other end also, we have to assign some flexural hinge here. Okay. Similarly, for the beam also, we have to assign flexural hinge at the ends. So this is the flexural hinge at the end here, and this is the flexural hinge in the beam, right? And this is the flexural hinge in the column. But remember, the only names are same, flexural hinge and flexural hinge. But property of the flexural hinge to be assigned for the column, its property is different than the flexural hinge to be assigned for the beam, because the interaction is different. For the beam, the interaction or degree of freedom is only M3. So in the software like SAP 2000, so the different flexural hinge with different degrees of freedoms are available. So user have to appropriately, correctly choose that particular hinge and then assign. For the beam, M3 type of the hinge is there. That is pure flexural type of the hinge is available. So we have to assign that hinge here. And for the column, even though it is a flexural hinge, but its interaction or degree of freedom is P, M2, M3, because column is subjected to axial load plus biaxial bending. Biaxial, M3, M2, and M3. So P, M2, M3, this type of hinge is available in the software. So for the column, we have to assign that hinge, must be assigned that hinge to the this particular end of the column. Similarly, for the shear hinge also. Okay, shear hinge is also not available ready-madely. We have to define some properties in the software, and that particular hinge for the beam, we have to assign side to the flexural hinge here at this location and at this location. Similarly, for the column also, we have to assign here shear hinge, and we have to assign the shear hinge. And now, since the shear resisting capacity of equations for the column and for the beams are different, therefore only the names are same, shear hinge, but the property of the shear hinge for the columns, the properties are different, and for the beams are different. Now, second approach, that is user defined hinge. If the ready-made hinge in the software is not available, then the user need to calculate the hinge properties. Now, calculate the hinge property, that means we required 4 values of the hinge. First is a moment at yield, moment at ultimate. Second is that rotation at yield and rotation at ultimate. Now, there are some codes are there, known as the one code is that Euro code 8. So in that, the 2 equations are given to calculate the rotation at yield, and on the next slide, rotation at ultimate. So rotation at yield. So these are the parameter. If the section is fixed, that is grade of the material, reinforcement configuration, grade of the reinforcement. If everything is fine, if it is known, then just substitute here. One more is, this is called as the length of the hinge. So equations are there. On the next slide, I will show equations are there to calculate the length of the hinge. And this red circled value is very influential value. Influential value. So this is called as the curvature value, curvature at yield. And how to get this value? Maybe you can use the knowledge from the basic structural analysis, or in SAP 2000, there is one command, what is called as a section designer command, section designer. So in the section designer command, just open it and create a model. Okay, create a model, that is create a model of a section of the column or beam. And what are the reinforcement at the top in the compression zone, and what is the reinforcement in the tension zone. Okay, and what is the this shear reinforcement configuration. Okay, so create this particular section in the section designer. Okay, and second thing is that then in at the top side there is one command, what is called as the this curvature, moment curvature relationship. Okay, moment curvature relationship. Then use that particular relationship. Okay, click on that, and then you will get this particular curve. Just I will show in the SAP also. Let the SAP 2000 to be open. Okay, meantime, I will explain the next part. So this is the equations, and from SAP 2000, we have to get this value, that is this rotation at yield value, not rotation, curvature at yield value. And second, this is the equation to calculate the ultimate rotation. Okay, so it is a ultimate rotation, theta u. Here also we require the curvature at ultimate and curvature at yield point. And again, this is LP, means length of the hinge. Then LP to calculate the length of the hinge. Again, many researchers were proposed the values to calculate the length of the hinge. Okay, in codes, different developing countries codes also proposed the equations to calculate the hinge length. But Montario study says that use any value, there is no much difference in the analysis result if you use any equation which is convenient for you. Then this is the next element, that is called as a beam column joint. So the beam column during earthquake behaves like a brittle. It fails under brittle failure, and this is because of the shear. Okay, so we have to assign the shear hinge at this particular junction. So shear hinge is also available in SAP 2000. Only user need to calculate the shear resisting capacity using the appropriate code, and just give one input to that particular this thing. I will show that also in SAP 2000, where this input is to be given. Okay. So these are the equations proposed by different codes to calculate the shear resisting capacity of the joint, interior joint, exterior joint equations are given. Okay, now this is the second thing, second element, what is called as a masonry. Sometimes we neglect the masonry, contribution of the masonry, and sometimes we consider the contribution of the masonry to resist the lateral load. If we are neglecting it, then there is no problem, not necessary to assign the non-linearity. But when we are considering the contribution of the masonry, then it becomes a structural type of the member, and we have to assign the non-linearity. It is observed that how the masonry fails during earthquake. So whenever the lateral load is there, that lateral load passed through the masonry in the diagonal direction. Okay, in the diagonal direction like this. So therefore, diagonal portion of the masonry fails under crushing, axial loading. It get crushed. So therefore, axial hinge, okay, showing this failure, we have to assign to the masonry. So it is an axial hinge. Therefore, assign the hinge at the center or assign the hinge at the ends. So this is pin connected. Mostly axial hinge is assigned at the ends, and this model is shown that when you create a model into a software, so this particular member is to be assigned with ends as the pin connected. As a pin connected, that means this is transferring only a lateral forces. Okay, and this is the portion of the masonry which is effective. Okay, so this is called the effective width of the masonry. So we require some equation to calculate the effective width of the masonry. So these are some equations proposed by the different researchers to calculate the width of the masonry. So use this in Indian code also, the equation IS 1893 equation is proposed to calculate the width of the masonry. Then in SAP 2000, to assign the axial hinge to that masonry element, axial hinge to the masonry element, we required some stress strain behavior of the masonry under lateral loading. Okay, so this is one curve. This is one stress strain curve proposed by Kaushik Rai and Jain in 2007 ASC paper. So it is their experimental studies, and the behavior of the masonry columns under lateral loading is represented in the form of a stress strain behavior. And this stress strain behavior values are required as an input to define the hinge properties. So in SAP 2000, these are some steps to define this hinge. Follow this particular step, go to define command, then section properties, then hinge property, add new hinge and axial hinge. Then this window opens, and then the stress strain values give here as the input. Okay, so same values are there in above this table and below this thing. So these are the values from stress strain curve. Okay, then hinge length here, input is 0.5. So that means if this is a diagonal element representing the masonry, so where we can assign the hinge, axial hinge at the middle also or at the ends also. Usually it is assigned at the ends. So what is the relative length? So just choose this particular option as a relative length of the member. The relative length in the sense, this is a 0, this is a 0, this is a 0, then this is a 0.5, and this is 1. Okay, so mostly the axial hinge is assigned at the middle. So therefore relative length will be equal to 0.5 as a 0.5. So this is the way by which the axial hinge to the masonry is to be assigned. Then modeling of the shear wall. Modeling of the shear wall. So shear wall, the modeling is done by two ways. First is modeling by means of it is assumed as a wide column. Okay. Now in this wide column approach, do not call it as a shear wall. Okay. You call this as the as a column only, having width is equals to thickness of the wall, that is 200 by 5000. It is a column, and the nonlinearity to the column, whatever the procedure we follow in the case of nonlinearity, assigning nonlinearity to the column in the lumped plasticity approach, same hinge is to be assigned to this shear wall also. Okay, there is no difference. Okay, this is the first approach. And second approach is that by means of a distributed plasticity approach. That means in the distributed plasticity approach, we have to assume the shear wall as the shell element, and we have to assign the nonlinearity for the complete area. So in the SAP 2000, there is one command what is called as the multi-layer shell element. Multi-layer shell element. So this particular command is that I will show that also in actual software. So these are the steps to assign the nonlinearity to distributed to the shear wall. So here everything is required to define thickness of the wall, reinforcement in outer face, inner face, including spacing of the reinforcement, and the nonlinearity. Are you assigning for in plane and out of plane? So that is also possible. We can assign it in plane nonlinearity as well as out of plane nonlinearity accordingly. So only thing is that before to use this particular the commands, the tables values, the user must be well aware of about the values. Okay, so this is about the nonlinear theoretical. Now coming to the software. Just I will open any one model. It is again taking some time to open it. But SAP 2000 is one of the good best software to assign the nonlinearity to perform the nonlinear analysis. I will open the building model. So this is a building model. Okay, first of all, I will show section designer, where actually this command is. So go to define. So here is the command, define command. Define. Go to define, section properties, and frame section. Frame section. Then add a new property. Go to add new property. And here go to other. go to other, and it is a section designer here. Go to other, and this is a section designer. It is other, and this is in a section property. So click on section designer. Click on section designer. Okay. Then here, define the RCC column section. M20, I was already defined it. So therefore, in this list, it is there. Here, give the name as the column section, say. It is a column. And click on concrete columns. Click on concrete columns. And second, here the user has a choice. Either reinforcement to be checked. If it is an old section, already reinforcement is there and you want to check it. Or reinforcement you have not designed and you want to design it. Okay, so I will go to the second, reinforcement to be designed, and click on section design. Now here, whatever this your section is there, so create a section. So this is a section is there, rectangle section. Then right click on the section. Right click on the section. Then you define the size of this thing. Suppose this column is of a 0.23, 0.5 is the height, and width is 0.3, for example. Width is a 0.3, 0.3. Then reinforcing. Click on a reinforcing. Yes, it is not a plain section. And again, there is two options: confined concrete or unconfined concrete. Okay, so both options are there. Okay, right now I will keep as a confined concrete, unconfined concrete. Then I will click on the, so this is the section is there. Okay, again, we can change the reinforcement configuration also. In my another video, I will show more detail about this. Then there is a now this is the option. Just click on this option to get a moment curvature. Click on a moment curvature. Sorry, I choose a wrong option. 1 minute. Let me check. Show the interaction surface. So this gives the interaction surface. This is option. To get a curvature value, to get a, this is the option. Just click on that option. Okay. Now this is a curve. This idealized curve. And this particular values are there. So this is moment value. This is the idealized. There are two curves. One is a curve is there, and then that curve is converted into a bilinear curve. What is called as the idealized curve. So this is the value at my, moment at yield point, and this is the moment at ultimate point. Moment at yield, moment at ultimate, these two. And curvature, corresponding values are curvature. This is a curvature value. Okay, this is, sorry. This is a curvature value. This is a curvature value at ultimate, and this is the curvature value at yield point. So in one click, just correctly design the section in section designer and click on this curve, you will get the value. Again, the reading of this value also we will get. If you click on that, this is the reading. Okay, these are the reading of the moment curvature value. So you can copy this into Excel and you can generate the curve at your own. Okay, so this is about the section designer. And about the hinges, ready-made hinges. So go to define section, then section property, and here it is hinge property. Section property and hinge property. Okay, and then add a new property. Click on add a new property, and we can define the hinge to the steel members, concrete members, or the members which are other than about two category is user defined. Then go to I will show to the concrete, add new property, and then click on concrete and say okay. Okay, so now first category is force controlled. First category, force control. So force control in the sense shear hinge. For the shear hinge, click on the first one. Select first. And when you click here, so force controlled, these many hinges are available. Category, axial hinge, shear V2, shear V3. For column, we have to assign shear V2, V3. For the beam, only one shear. That is a V2 type. For the beam, only V2 type. That is shear force in the vertical direction. Right. For the column, we have to assign the shear hinge V2 as well as V3 because it has two faces. So this comes under force control. Okay, just I will click on any one shear hinge. Okay, and then it is very easily we can assign the define this property. Okay, so here we have to assign the shear resisting capacity of the hinge. Okay, shear resisting capacity of the hinge. Default value is 1, but by using codal equation, calculate shear resisting capacity value and then just input and say okay. This is about the shear hinge. And second is a deformation control hinge. Mostly flexural hinge is a deformation control hinge. Then click on that, click on this, and under deformation control hinge, these many hinges are available. Okay, especially for the beam, we have to assign M3 type of hinge. M3 type of the hinge, because the beam deformation is with respect to, this is the beam deformation. So this rotation is with respect to axis 3,3 in SAP 2000. So therefore, we have to assign M3 degree of freedom. While as for the column, we have to assign this hinge. If it is a 3D model, then we have to assign P, M2, M3, this type of the hinge. So this is also available. Just I will show the details about P, M2, M3. Just click it, then OK. So in one click, we can assign these are the ready-made hinges are available, but at the back end, the software do the calculation. That is, there is a very vast calculation is there. So it define all these particular values. Just superficially, I'm showing this thing. Then this is the moment curvature surface. For different curves. Okay, so these are the different values. So in the SAP, if this is 10-story building is there. So to 10-story building, within a 5 to 10 minutes, we can assign the non-linearity to all these major structural element by using a ready-made hinges. Okay, so this is the topic for the today's discussion. Okay, so we have discussed about the non-linearity, that is geometric. At the end also, I will say one thing about the geometric non-linearity also. So geometric non-linearity, that is a P delta effect. So it is to be, the option is here. So go to load case, go to load case. Then for example, time history load case is there already, which is defined, and just modify this. Just modify this time history load case, and here is the option about the geometry. So none, in the sense the P delta effect is not necessary. It is not influencing P delta effect. And third option is P delta plus large displacement. Okay, so the P delta and P delta with large displacement, this is just two options to solve the equilibrium equations. So either you can go for P delta or P delta plus large displacement. In the case of large displacement, that is third option, the stiffness matrix gets update in every step. As the material goes on cracking, the stiffness goes on reducing. Therefore, it affects on the stiffness matrix. So every step it calculate the P delta, and that new stiffness value, it takes that calculation of that particular step. While as in the case of P delta, it calculates the stiffness at once. Okay, and that is in the same value is used for the rest of the calculations. So therefore, P delta plus large displacement, it will take more effect. But the user need not necessarily to worry about this value, because not necessarily do the calculation, software automatically does it. You just select this particular option. Okay, so this is about the non-linearity and some insights into SAP 2000 software. So thank you for listening. Thank you.